Hello everyone. Uh, Welcome to all of you on my YouTube channel. So here in this session, I'm going to discuss about one parameter model. Already I've completed the zero parameter model that is based on the complete segregation model and a maximum mixedness model in my previous lecture. Okay. So from here in this lecture, I will be starting from the one parameter model, and in one parameter model, I will be discussing from tank in series model and axial dispersion model. Okay, so these are the two models that is very important for our gate examination and as well as your bachelor's semester point of view. Okay, so if you are getting these things, then it will be enough, more than enough for you to solve the problem. So let's try to understand, my dear student, one parameter model. Okay. So one parameter model. So first is tank and series model. Already I have discussed all these things. So it's very important. Very frequently you will see there is question that is coming in the gate examination or in even if in the bark on this model actually. Even if in 2022 the question was also on the modeling parameters. Okay. So in this here, tank and series model is used for analyze the behavior of PFR. So here you can write it is used to analyze the behavior of PFR. Okay, so directly you can write the parameter will be number of tanks. It's very important that you need to understand here the parameter will be number of tanks. Okay, so now I am considering let n number of CSTR are connected in series. After that, I will let you know the objective of these things. Just try to understand the thing. Here, there is CSTR, there is inlet, and all the CSTR are connected over here is having same volume. Okay, it is my assumption over here because the thing becomes very easy. So the outlet, and again here it is series. Again here it will be coming in this way. Again here it will be coming in this way. Again here it will be coming, and there is shown number of CSTR will be there, and here okay, it is outlet. Okay, so CSTR is well known for the continuous steering as well as uniform mixing. Okay, so that's why there will be a steerer over here. Okay, now here I am assuming the volume of the CSTR is V and V. Okay, and so here it will be tau 1 is equals to tau 2 is equals to tau 3 is equals to tau 4 and dot this is equals to tau n. So the residence time for all the CSTR will be same. Okay. Next, my dear student, for one parameter, so for pulse tracer input will be applied. For one parameter model, pulse tracer experiment will be performed. Okay, on the inlet of CSTR. That is, you can say first CSTR. Are you getting? Next, so when we talk about, my dear student, here here it is concentration. If you are assuming C naught, here concentration is C1, here it will be C2, here it will be C3, here it will be C4, and dot dot here it will be Cn. So what will be the value of C1 from here? So can I write C1 that is equal to C naught and e to the power minus of t by tau 1? Are you getting? So can I write my relation E1t that is RTT curve that is equals to 1 upon tau I e to the power minus t by tau I. That you know, this is the basic things in the CSTR and PF continuous state tank reactor. This is concentration at the exit, and this is the exit age distribution function. This is very important that you should know. Okay. Now moving further, when we talk about I mean for second reactor. So can I write my distance C1 into V naught? Why? Because here, just try to understand here, I am considering volumetric flow rate will be same. So C1 and here it is V naught. I am assuming mass balance over here. So C1 into V naught, okay, that is mole balance. Generally, you can apply the mole balance and mass. C1 into V naught minus C2 into V naught. This is in minus this is out. So you can write in minus out plus generation minus consumption, that is equals to, it is a rule of thumb for any reactor of mass balance and mole balance of these things. So here moles of tracer in minus moles of tracer out. Okay, there is no any generation consumption of these things, that is equals to accumulation, that is equals to V, and that is equals to dC2 upon dt at the exit of the reactor. Are you getting? That is in, that is out, and that is accumulation. Okay, so C1 you can write that is C naught into e to the power minus t by tau 1 and into V naught minus C2 V naught, that is equals to V dC2 upon dt. Are you getting? So next, can I write C naught e to the power minus t by tau 1 minus C2, that is equals to V by V naught dC2 upon dt. Why? I have taken common V naught and after that I placed over here. Can I write again C naught e to the power minus t by tau 1 minus C2, that is equals to tau and dC2 upon dt. Generally I am writing the tau I. Okay, tau I. So can I write over here C naught e to the power minus t by tau I upon tau I. Okay, minus C2 by tau I, that is equals to dC2 upon dt. So can I write C naught, can I write directly dC2 upon dt plus C2 by tau I minus C naught e to the power minus t by tau I upon tau I, that is equals to 0. So can you see here, this is a differential equation. This is a differential equation, linear differential equation of constant coefficient. Okay, so dC2 upon dt plus C2 tau by tau I. This is linear differential equation. So you'll have to solve this differential equation, and you all are very dexterous in calculating this differential equation. It will be calculated by calculating integrating factor, and it is equal to e to the power 1 upon tau I dt. So that is equal to e to the power t upon tau I. So finally you have calculated the, my dear friend, the integrating factor also. Now the thing will be very easy for you. So once after calculation integrating factor, we'll move forward to solve the problem. Can I write C2 into integrating factor, that is equals to, if you are assuming this is in the form of this, that is equals to dC2 upon dt plus C2 upon tau I, that is equals to C naught e to the power minus t by tau I upon tau I. So if I am assuming this one as Q, okay, Q, that is the general procedure of solving this differential equation. So can I write here q multiplied with integrating factor and it is equals to dt. So can I write again C2 and integrating factor is equal to it is what t by tau I, that is equals to C naught e to the power minus t by tau I, okay, upon tau I and e to the power t by tau I dt. Are you getting? So you can calculate this in. So can I write again C2 e to the power t by tau I. So once we do the calculation, so this is the tau I, C naught by tau I will get common. So it will be equals to C naught and t upon tau I plus you can write k. This is a constant. Okay. So at t is equals to 0, C naught is equals to 0. Are you getting? Sorry, C2 is equals to 0. If C2 is equals to 0 and t is equals to 0, so k will be equals to 0. This is our boundary condition. So I mean no C2 will be there at t is equals to 0. So can I write C2 e to the power t by tau I, that is equals to C naught t by tau I. Are you getting? So our objective is calculate C2. Okay. So our objective is to calculate C2. Finally you have got C2. This is the function of time, that is equals to C naught t by tau I e to the power minus t by tau I. Are you getting? C naught t by tau I and e to the power minus t by tau I. So now you will have to understand there is a recurrence relation there in between the outlet concentration of every reactor. So I am writing the recurrence relation. So if you will write C3T, you will be getting C naught upon factorial 2 tau I square t square e to the power minus t by tau I. So you can understand the relation. There is a recurrence relation that you can see over here. So I am writing directly CNT, that is equal to C naught, okay, upon t by tau I whole to the power n. And here you can see if here it is 3, here there is a factorial of 2, means 3 minus 1 factorial. So here you can write n minus 1 factorial. Are you getting? Here there is a n minus 1 factorial. It is factorial sign. Okay, I am writing over here. And e to the power minus t by tau I. Again I am writing here, that is CNT, that is equal to C naught upon n minus 1 factorial n2 t by tau I whole to the power n e to the power minus of t by tau. Okay. So this is the recurrence relation and you can calculate the concentration at the exit of any particular reactor. Are you getting? So my dear student, you can see at t is equals to n is at t is equals to 0. At t is equals to 0, concentration will be 0, and t is equals to infinity, again it will be 0. Are you getting? So at t is equals to 0, Cn is equals to 0, and at t is equals to infinity, again Cn is equals to 0. Sorry. So I mean there definitely there must be a I mean the curve will be increasing and again decreasing. There must be a maxima. Okay. So I mean you can calculate the thing from here. The plot will be like that. A plot will be like that. If here it is Ct and here if it is time, so the plot will vary in this way. It will be 0 initially, it will go to maxima, and again it will come to 0. Are you getting? So this is the concentration versus time curve for n CSTR in series. Okay. Now when we talk about, my dear student, ET, okay, E2T, E1T we have calculated. So can I write T into e to the power minus T upon tau I divided by T and multiplied with e to the power minus T by tau I minus d upon dt of T and again e to the power minus T by tau I. It's as simple as that. This is just an integration. Okay. So finally you will be getting T upon tau I square and e to the power minus t by tau I, e to the power minus t by tau I. So finally, you can calculate E3t also, and that is equal to t square upon tau I cube and factorial 2, okay, and e to the power minus t by tau I. That you don't need to derive everything. Here I am deriving to let you know. So again, you can see there is something related to this one and this one. So you can see there is any expectation of the recurrence relation. So I am writing here the recurrence relation. So directly I am writing ENT, that is equals to my relation t to the power n minus 1 upon tau I equal to the power n minus 1 factorial and e to the power minus t by tau I. Are you getting? E to the power minus t by tau I. So here this is the recurrence relation of this particular thing. Okay, for RTD function. This is our RTD function of nth order reactor in series. RTD function. Are you getting? So we have calculated, you have derived the RTD function now. Now try to understand one thing, my dear friend. What is happening? The mechanism is very important over here. I am letting you to know with the help of the graph. Then it will be very easy to visualize you. So if I am telling you it is ET and if it is T plot, if it is ET and if it is T plot, so finally when n is equals to 1, the plot will be varying like this. You can see the plot is going like this, ET versus T curve. Are you getting? When n is equals to 1. When n is equals to 2, the plot will be coming like this. There is a broad plot like this. And again it will be going like this. When here I am writing when n is equals to 1, when n is equals to 2. Are you getting? Again I am telling you when n is equals to 3, it will go like this. It is when n equals to 3. Again I am writing this plot is when n is equals to 4. Okay. Green is when n is equals to 5. Okay. And you can see there will be a plot like this one when n is equals to infinity. So when we talk about a ET curve of PFR, ET versus T curve of it is PFR, how it look like, you will just try to understand. It used to be look like this one. It is a direct delta function. And again here you also see when n is equals to infinity, when n is equals to infinity, it also looks like this. So the plot will be like this. So can I say here from the plot when n CSTR having equal volume connected in series will work like a single PFR. Are you getting? So this is the objective of this session, that how this n CSTR having same volume when we are connecting it in the series, then they will work as a no, the PFR. Okay, so this was the objective of this thing. So hope I have tried my best to let you understand your thing, how these things work like that. Okay, so I think up to this, uh, everyone is very clear. All of the thing that I have let you understand. in the tank in series model, and how we can derive the thing, how we can calculate the concentration at the exit of any reactor, how we can calculate the RTD function at the exit of any reactor, and how the number of series and CSTR connected in series will work like a PFR graphically. Okay, so in the next lecture, I will be discussing how we can calculate the number of times and how we can calculate the conversion from NCSTR connected in series. Okay, so thank you for all. Thank you for watching this video. And if you are facing any doubt, you just go through this video, and you'll let you get to know how we can solve the problem on the basis of this concept. And at the end of this session, when I will be completing the one parameter model, I will solve some numerical problems. So from there you can get a good idea how we can solve the numerical from this particular concept. Okay, so thank you all.